but I think we should get going. For those of you who don't know him, this is Maxim Shcherbakov. He did his master's and PhD at Moscow State University before moving to New York. And now he is newly appointed faculty this year at UCI. His research merges fundamental physics concepts and cutting-edge nanotechnology to innovate in the area of photonic devices. And you can tell that I'm directly quoting from his website there. So the idea is to give design nanomaterials with unprecedented flexibility to manipulate light waves on demand. So this is a very sort of hot topic in photonics, all of these things. He's done a lot of very interesting work so far. He's very much a bit of a prodigy. So we're really excited to have him here at BLI and listen to what he has to say. So Maxim, I'm gonna hand over to you now.
That was quite an introduction, Daryl. Thank you very much. I do appreciate it. And also thank you for hosting me and inviting to give this talk to all the interested in nanostructures as they interact with light and laser radiation. I wanted to give this talk for a long time because I feel like a lot of my research can speak to the research areas and areas of interest at BLI, and reciprocally, I'm very much into trying to extend the research that I do and that my group does to some of the biomedical concepts that a lot of you work in and really are prosperous as researchers. So today, I wanted to give my perspective on some of the research that I did in the past as a newly appointed faculty. Of course, I would mostly be talking about research that I did as a part of my postdoc, as a part of my PhD, maybe. But all of this, all these ideas and all of these concepts truly follow through in my research agenda. And many of these things I'm still very much interested in on one hand, and on the other hand, I think they're very relevant to the research topics here at BLI. And the title of my talk is here on the first slide. And please feel free to stop me at any point. I would love to have some interesting questions and to have really a discussion of how my research could be helpful to you as a project leader, as a postdoc, as a student, and how we can keep talking about these things and maybe come up with some exciting new ideas together. I will be talking about photonic nanostructures. This has been the bread and butter of my research for a long time now. I am interested in the ways how you can make light interact with matter in an unprecedented, in a surprising and maybe interesting way that nobody has ever thought about before. And I do so by creating and designing and fabricating nanostructures of various shapes, forms, materials, and other parameters. And today I'm just gonna bring up a couple of examples of what we've done in the past and how we can, save these concepts and do something even more interesting later. And the basic motivation, I think, behind my research has always been the fact that nanotechnology has changed a lot in our lives and the lives of our parents, grandparents, even some of them, by just taking a piece of bulk material that in itself maybe not as interesting as it could, and by imposing some nanostructuring onto this material, we can truly come up with contraptions that have changed lives of generations now in nanoelectronics, microelectronics specifically. And being inspired by this idea of nanostructured materials getting new properties and bringing new functionalities that were not there before in electronics, my research translates to this idea and blends in a vast research area where we do the very same things for photonics, for light-based devices. And the most basic idea here would be to try to maybe reinvent some of the basic optical elements, such as lenses that are used to be everywhere in a bulk form, not until recently. Having been invited thousands of years ago, people started thinking about how we can change, how we can miniaturize some of these devices, and how we can make them smaller, lighter, and more applicable to some of the areas that bulk optics were not really truly reaching to. And part of the solution here to reduce the size of the lens of a classical bulk optical lens is to make it flat through the concept of diffractive optics. And by just changing the geometry, by just changing the size of the device, you can tremendously reduce the dimension and the weight of the device, as seen in lighthouses, as seen as automobile headlights and other places where you get very similar functionality, but in a much thinner footprint. And it's only been recently, maybe in the past 10 years or so, where the research field of nano optics has actually pushed the limit of the thickness for these devices to I would say, the ultimate limit of thickness, where these elements have reached thicknesses of approximately one wavelength in size. So here is just one of the examples where, by nanostructuring thin gold films with a thickness of about maybe 10 to 50 nanometers, you can recreate the phase profiles required for diffractive optics elements, but keeping the thickness of these devices much smaller. And started as a purely fundamental interest in the area of photonics. This area has now grown to a, I would say, industrially successful case, where some of the first startup companies have started attracting significant funding to replace, again, as an end goal, to replace bulk large optical elements with something that is extremely thin. Why would anybody be interested in this? And why are we excited about the prospect of trying to reduce the size and weight of optical elements in general? There are multiple reasons for this. One of them is, wherever you want to try to reduce the size of your imaging element, of your imaging system, such as a mobile camera, you can immediately see that the thickness, for instance, in cell phone cameras, are purely determined by the, not purely, but for the most part, determined by the size of the optical system and a lens in particular. And that applies to many other applications, such as night vision devices, mixed reality devices. If you want to send it into air, into space, your optical element must be as light and as small as possible. And nanostructured optical elements can alleviate this issue of having somewhat bulky optical systems that are used these days. So in many applications, reduced size and weight is critical. And myself and many other researchers in this field, including those at BLI, are very much interested in addressing these issues. And speaking of some of the ideas, some of the results, and some of the projects that I'm interested in, here's a broad roadmap for research in my group. We start off with nanostructured materials. As I mentioned, I'm going to be talking about what kind of structures, what kind of materials we are using in detail. But just as a general bird's eye view of our program, we start off with these materials as a platform. we apply some of the advanced concepts in light matter interactions. I'm going to be briefly talking about these two today. And as an end goal and as a sort of light at the end of the tunnel, we are envisioning the end result as a device that can be applied to realistic use case scenarios in optical technology. Today, I'm going to be talking about several examples. I will start by briefly overviewing the idea of a photonic switch, where we want to be able to make photons interact with one another. And many of you know that this is usually done through optical nonlinearities, which are traditionally small. And I'm going to show you an example of a structure that can partially alleviate the issue of weak photon-photon interactions. I will then move to a somewhat more relevant area, specifically to BLI research in imaging elements that are tunable. Here we will merge the idea of nanostructured lens that I showed to you a couple of slides ago with a well-established technology of liquid crystal research, and we will create a varifocal lens based on this nanostructure. And if I have time, I also would like to share with you some of our most recent results in light matter interactions at the nanoscale, where we showed that these designer nanostructures can actually assist with deep subwavelength nanomachining. I think that nanomachining is the most appropriate word here. And I would like to kick off with the project on photonic switches, where the idea is very, very simple. As I mentioned, the basic element of any digital logic in electronics is a switch where you can control one input signal, be it electronic signal or photonic signal, that is initially DC, and by applying a control series of pulses, you can modulate this DC signal with the series of bits that you want to encode on it, with the help of a device called a switch. And in this basic configuration in electronics, it is done either mechanically or electrically. A very well-known device to be used in nano and micro technology. However, for optical switches, there's been a certain there have been several setbacks that did not allow for creating of these kind of devices, and part of the motivation here is to try to come up with a structure that can act as a photonic switch. Of course, we stand on the shoulders of giants. There's been a lot of effort of building photonic switches where an input photon can control the other input photon and modulate its transmission as part of this idea of all optical information processing. What we wanted to do in our research as a first idea is to try to minimize the size that this photonic structure occupies by using really small particles made out of amorphous silicon in this instance. And the reason behind why we thought we will succeed in using these particles is that they actually, if they're made of a high index material, which amorphous silicon certainly is a high index material, these particles, being truly subwavelength in dimensions, can still have resonances and basically boost nonlinear interactions and boost photon-photon interactions that are required to create an efficient optical switch. And here we basically built upon a very well-known theory of light scattering of a sphere that has been established more than 100 years ago. But one fact that was overlooked at that time, or rather at the time of experimental addressing of this problem, was that the fundamental resonance of a spherical particle is actually a magnetic dipolar resonance. And it is also a very interesting one because field gets concentrated within this particle, making photon-photon interactions, again, very efficient. And one of the demonstrations of why this is important, why we thought it would work, actually was demonstrated not long ago in a famous gray plasma experiment, where two gray particles that are subwavelength for microwave being put in a microwave oven create a strong electromagnetic wave matter interaction by creating this kind of plasma burst. As a disclaimer, I would urge you not to try this at home, because you will ruin your microwave, or you have a very high chance of ruining the microwave. But this just shows to, the idea here is that by using these fundamental resonances of dielectric spheres or dielectric particles that are deeply subwavelength, you can enhance light matter interactions and hence promote photon-photon interactions through these light matter interactions. And I've been interested in nonlinear optics for a long time. I know specifically in this room, there are a lot of people who contributed significantly to the area of nonlinear photonics. Part of my research was always devoted to trying to see how photons can merge in nanostructures. And recently we've shown that these nanostructured surfaces, which we sometimes call metasurfaces, can merge multiple mid-infrared photons together to produce a rich variety of high harmonic generation signals that is actually very, very efficient. And this whole concept of resonant nanoparticles actually can boost nonlinear light matter interactions to a high degree. So going back to the idea of photonic switches and light interactions within these nanoparticles, we did a simple experiment. We, again, as part of the platform where we can use multiple materials and structure them at the nanoscale, we proceeded to fabricate for this particular project a series of photonic samples using methods such as PCVD and electron beam lithography. Here's a simplified fabrication flow for this kind of sample production. And we ended up having an array of small particles made of amorphous silicon. Again, we have capabilities and we have expertise in fabricating structures out of various materials. My focus is mostly in semiconductors, which may come in handy with the ongoing limitation on semiconductor foundry fabrications, and we do have extensive expertise in making nanostructures out of silicon, germanium, amorphous silicon, amorphous germanium, 3,5s, gallium arsenide, aluminum gallium arsenide, and other materials. But recently we've been working with a silicon nitride, silicon-rich silicon nitride. That's an interesting one. Dielectrics of other sorts, such as silica, and some of the 2D materials as well. So if you have interest, if you have any applications in mind where you would love to work with a nanostructure of a specific shape or form, please feel free to reach out. We sure can work together, especially if this is related to enhancing light matter interactions at the nanoscale. So getting back to the photonic switch idea here, we use these samples to just to see how fast one photon pulse can interact with another photon pulse. We use femtosecond laser pulses as a source because this is the fastest way to check if your device is fast enough for your application. And a simple pump probe experiment was done here. We've used a train of 45 femtosecond pulses to get a two-beam experiment where there's a probe pulse and a pump pulse, and the sample was irradiated by two of these pulses simultaneously. And our raw idea here was that let's see how fast of a response can you get. And the initial trace showing how one torrent of photons interacts or with another torrent of photons here on the picosecond scale showed two typical time scales, I would say. One was slow on the pico, 10 with a relaxation of about 10 to 100 picoseconds, and one was very fast, basically as fast as the duration of the pulse. And our goal was to try to minimize the slow component and to maximize the fast component. And we did that by engineering the size of the particle. So just by changing the radius of the particle here, we can go to switching events that are less than 100 femtosecond long. This is kind of a busy slide, but basically what we're looking here is this spike here on the left top of the slide. This is the pump probe trace on the femtosecond scale, and it shows that only the dip at the sub 100 femtosecond time scale is present, and no slow contribution that we saw previously was demonstrated here, which means by changing the dimension of the particles, or in general by applying ideas of nanoengineering, you can come up with scenarios that were not possible in bulk materials. Because if you were to work with a bulk silicon material, you would always see this slow component that will decrease the speed, the operational speed of the device. And at that time, this structure used to be the fastest and the smallest photonic switch that was reported. It's been quite a while now. Other geometries and other material platforms have emerged, but we were proud to demonstrate that resonant silicon nanoparticles can serve as a very efficient and very fast photonic switches for all optical signal processing. Now I'm gonna shift gears just to follow up on this one. We are still continuing this research with my colleagues from Cornell and trying to come up with the ways of create a photonic simulator, photonic quantum computer, and narrow version of a photonic quantum computer where you can simulate the Hamiltonian after preparing an initial state in one part of the chip, and then addressing individual particles as they are arranged on this particular chip to create the simulation of a certain Hamiltonian. And this is in the making, but we're very, very excited of the prospects that silicon nanoparticles can bring to quantum simulation. Now, as I mentioned, to switch gears, I wanted now to talk to you about the ways to create compact imaging elements, such as lens, that are also at the same time tunable by external stimuli. And just to recap why we're interested in that, if you ever saw a camera, or if you ever owned a camera, you know that the way to create focus at a certain scene at a certain distance from the imaging element is usually to move the optical elements, such as lenses, around in a mechanical way, right? Just replacing them in space, reconfiguring the overall focal distance of the lens creates conditions for varifocal operation and varifocal and mechanically tunable zoom, right? And mechanical actuation of the focal distance is okay for some applications, such as cameras, but at other instances, you would imagine that you would love to have a focal distance that is tuned non-mechanically, because it drastically reduces the size and the weight of your imaging system. So imagine if you could potentially have this objective and replace it with just one optical element that has a variable focal distance, and that this focal distance can be tuned electrically. For instance, this is the imaging solution that Facebook develops now, and for their VR glasses. And you can see that there's an imaging lens, and there's a mechanical actuator that moves the lens back and forth, which it presents a certain set of challenges. First of all, because this system is somewhat heavy, but also the limited resource of mechanically actuated systems is a well-known problem. So what we want to do is to make a step toward creating imaging systems that are on one hand flat and on the other hand tunable. And we will do so with the concept of a meta lens, which I introduced earlier. But basically, to recap here, the concept of meta lenses or metasurface based lenses, nanophotonic lenses, there are many names for this, is that you start with a thin optical device, basically a diffractive optical device that is as thick as a single wavelength, maybe a couple of wavelengths, where the phase of the wave that is coming through this device is coordinate dependent. And this phase is determined by the shape of the particle that exists at a certain position. So at the output, if you had a plane wave coming in, it becomes a converging wave that creates a focal point at a certain distance that is also determined by the geometry of these particles. It's basically very much very similar to a phased array antenna in RF, where it is very easy to tune the phase delays between several antennas by just electrically addressing them. However, the problem with optical systems and optical meta lenses specifically is that after you've fabricated this device, the focal distance is fixed by the dimensions of these particles. So creating a very focal meta lens has been a challenge for quite some time now. There are several approaches how you can create tunability for these kind of lenses, but pretty much obviously the best way to address this problem would be to apply electric fields. And for that, we switched to a very common, very industrially successful platform that supports electrical switching, and that is the liquid crystal technology, where I'm pretty sure most of you know, the molecules of liquid crystal can be reoriented by applying electric fields and basically change the refractive index of the material that is in contact with a future metasurface. And when I say changing refractive index is just by just the virtue of reorienting the tensor of the liquid crystal molecules. And this idea has been brought to life by a student at Cornell with whom I had I enjoyed working while I was a postdoc there. And basically what Melissa did here, she fabricated the nanoparticles that are shown here in white. These nanoparticles would create the conditions for focusing. And then on top of that, by working with Samsung Electronics liquid crystal lab, we've encapsulated this metasurface into a liquid crystal cell that went into the direct contact with the nanoparticles. And then by applying external voltages, you can switch the orientation of these liquid crystal molecules shown here in blue from horizontal to vertical, for instance, and that would create different phase profiles engineered onto these particles. Here they're shown in a little bit of a zoom in form. They're based on amorphous silicon. Again, this is a material of choice for a lot of our experiments. And again, by changing the dimensions of these particles, you can impose a certain phase map, which then can switch between on and off states as you apply voltages to your liquid crystal cell. As a result, we've first designed this in theory with full wave simulations that you can change the focal distance of this element from, for instance, -f to f by reorienting the liquid crystal molecules within liquid crystal cell. So here the change in the focal distance is discrete, and by applying voltages, you can go from about -8 millimeters to 8 millimeters with very high efficiency. All the energy will go directly to the focal spot of interest. And experimentally, this is our first experiment from about a year and a half ago, where the energy has been redistributed between two focal spots, although the efficiency here was at that time of about 50%. So this particular sample was not up to really creating very good images between plus f and minus f. And additionally, experimentally, we've demonstrated a lens that can change the focal distance continuously, which was a challenge too. If you want to install it on your camera, if you want to install it on your AR glasses, it must be gradually changing the focal distance. And this is what we demonstrated by designing a specific meta lens that can do this. And quite recently, by optimizing the structure, Vilas has shown resilience of overcoming many obstacles, trying to make the best of the situation in terms of intensities. And she finally came up with a sample that can actually shift between several scenes, two scenes, and showing, for instance, here an image of a test target f at f/2 at a focal distance of about 5 millimeters, and then by shifting the liquid crystal molecule orientation, all the energy, most of the energy goes to the focal spot of f, basically doubling the focal distance of the system by applying voltage to this very thin optical element. And if you compare to state-of-the-art, liquid crystal lenses have been there for quite a while. If you're interested in this, there is an excellent review on this topic where there are many geometries of how you can create varifocal lenses coupled to liquid crystal molecules. However, by coupling this system to a meta lens, to a nanophotonic, nanostructure-based optical element, we've demonstrated the highest optical power to thickness ratio, meaning that our lens is thin. It's only about 5 micron thick. The whole liquid crystal cell is only about 5 micron thick. And its focal distance is very short. Usually there would be a certain trade-off if you were to use conventional liquid crystal devices. And this research has been, as I mentioned, sponsored by Samsung Electronics, where we hope that our patented technology will at some point make it to augmented reality devices that, to the best of my knowledge, they are working currently on. If there's any questions at this point, before I switch to the next topic of my talk, please feel free to stop me here, and that would be a good time to ask them.
Yeah, Maxim, thank you. This is really very interesting. Tom Milner here. So
Hi, Tom.
what wavelengths are these liquid crystal lens? Where do they operate in the spectrum?
Our first experimental samples were designed and operated at 800 nanometers. And this is a trade-off between multiple factors that factor in here. If you go back, we use ITO electrodes, so we cannot go too much into IR. And on the other hand, amorphous silicon imposes certain limitations on using them in the visible. So these were for 800 nanometers. Currently, yeah, but right now we are actually working on using a different material based on silicon nitride, and we were successful in showing very similar structures on that operate at 600 nanometers, and now we're working at 550. So we're slowly moving to the visible, where you can actually create devices that can work with your natural vision. Additionally, and importantly, though, there are ways of how you can extend this idea to infrared by replacing electrodes with a different material. This is not a big deal. For instance, we are, as I'll show later, we are very much interested in the mid-infrared. And in the mid-infrared, these structures can also be realized, although instead of a liquid crystal, you will have to use something else. But we have ideas how to get there.
Thank you. Yeah, a lot of the tissue optics is done, out in the IR.
Mm-hmm. And what wavelengths would you be most excited about?
For tissue optics, like 1.3 is a common one, 1.7, anywhere out there past 1, but less than 1.78 microns is those are for tissue optics. Those are interesting wavelengths. Not to say the ones in the shorter than that aren't interesting, because they are, but it's just the scattering. Scattering tends to decrease substantially once you get out into the 1.3, 1.4, 1.5, 1.6, 1.7 range.
Yep. So this is actually very much doable, I would say, because liquid crystals, as far as I know, they're still okay at these wavelengths. They do not start absorbing through organic bond vibration. Maybe not E7, but maybe some other liquid crystals. The only limitation here would be the ITO electrodes, but these could be replaced with just n-doped silicon, no problem.
Yeah, no, I didn't, and it certainly didn't mean to imply that these other wavelengths aren't interesting, because they certainly are for tissue optics. But yeah, so I didn't want, don't want to. They are. I mean, like 800 is a very useful, interesting wavelength.
Well, thanks a lot. It gives me a perspective on what kind of wavelengths we're talking about here, and where this effort could continue. Thank you very much. Thank you.
Max, I was just wondering what the variation in focal length you can get is as well. Can you change that quite substantially?
I would say it is fairly substantial. You can flip it from -f to f. So if you start off with 10 millimeter of a focal length, the switched on state would be -10 millimeters, which if inserted in a complicated optical system can do amazing things. But that would be a discrete switching. So here you will be switching from -f to f, and that's it. The other configuration would be switching the focal distance continuously, and that has a somewhat narrower tuning range. But so our first report was showing about 20% of focal distance change, which is again a pretty substantial, in my opinion, a pretty substantial change. And I think that the ceiling for this method would be in about, just intuitively, at about maybe 40%, 40 to 50%.
Hi, this is Zhongping. I have a question.
Hi, Zhongping.
And where the matte lens also can get diffraction limited focus?
Yes. These are, I would say, surprisingly good for a diffractive optical device. The Strel ratios we're getting, they're pretty high. We've never, they're if you go to this particular paper, we analyzed this, and the spots are very close to diffraction limited.
Okay. How fast those liquid crystal can change the focal length on the 100 hertz or kilohertz?
I would say 100 hertz is a viable frequency. 100 kilohertz is probably not. So it would be somewhere between those.
Okay. Thank you.
Yep. All right. So
hey, sorry, I just had one more question, if that's okay.
Of course.
Yeah, so you mentioned using these for things like VR glasses and stuff. How would the structures work for different wavelengths at the same time?
That's an excellent question. Our goal here is to create structures that can operate at 3 different wavelengths. And we are slowly moving toward this goal. Right now, we have designs of liquid crystal metal lenses that work at 2 wavelengths, 635 and 550. And eventually we'll get there to the blue. So operating at 3 discrete wavelengths is very much possible, and I think it's a matter of time when we'll come up with this. However, it's very important to understand that these structures cannot work with a broadband signal, as in covering all the wavelengths in the visible spectrum. So 3 wavelengths is something that's possible. That's something that we do, and we'll soon get there, maybe in a half a year or so.
Cool, thanks.
Yep. All right. So if there are no questions at this point, let me move to the next topic and switch gears a little bit. But if you would like to post address this, feel free to reach out. Just before going into nanomachining, this is an overview of different ways of how you can tune the optical properties of these structures. The one that I went into details here was to reorder liquid crystal molecules, and this is the typical time scale as discussed. So it's in some maybe tens of milliseconds. There are other ways how you can tune structures, and that is using heat, which would be slow, but in some instances very efficient. You can do electrogating, you can do all optical free carrier injection, but basically most of the time scales that are somewhat applicable to photonic devices can be covered, and we are actively working in this area to specifically address some problems related to all optical light wave control, and maybe at some point coming up with an idea of how to create a 4-dimensional microscope where time is another degree of freedom, and you can control light fields basically in 4 dimensions. Now, I have about maybe 10 minutes, and these 10 minutes I wanted to devote to another topic, which is a little bit different from what I was talking about before. Before that, we were manipulating light with nanostructures. Here, we will be manipulating nanostructures with light. And these are very recent results that my colleagues and I have obtained with in a collaboration between Cornell, Ohio State University, and myself. And I think that in the context of biomedical engineering and laser medicine, these results can be interesting. They are related to laser damage at the nanoscale. And the idea behind that is we very well know that using high power laser pulses is one way to mechanically modify materials. And there are several regimes that people have used before, in that sending a single femtosecond laser pulse can create very small subwavelength features in dielectrics. Sending multiple pulses onto materials can also create some very small and very fine details in otherwise homogeneous materials. And both these regimes have created several ways of nanostructuring media. However, most of the time, what people would do is they would use focused laser pulses, which are maybe Gaussian, but most of the time diffraction limited. And the final dimensions of what you can get from these experiments is determined by the size of the beam. Now, if we go back to the idea of using nanostructures to modify light beam profiles, we would recall that, again, using this idea of high power, deep subwavelength laser energy concentration, or electromagnetic wave energy concentration, we can infer that nanomachining could benefit greatly from localized hotspots that can be created with these nanostructures. So the idea here in this particular effort is to use prefabricated structures with certain hotspot local field distributions to assist with deep subwavelength laser nanomachining. And for this particular experiment, what we did is we started with prefabricated particle of a specific shape. I won't go into too much of a detail of why exactly we chose this shape, but the main idea here is that this particular shape will create a certain electric field hotspot at the apex of this V-shaped formation. And this hotspot will seed the process of nanomachining. And after irradiating this structure with a mid-infrared laser pulse train, we used the 3.6 micron as an example, we will end up having a certain nanoscale modification for this structure, which has a typical critical dimension much less than the wavelength that we used, because we created this hotspot in the first place. The samples for this particular experiment, we fabricated out of a silicon or sapphire wafer, which is a very sturdy kind of material. I would say much more resilient to laser radiation that compared to maybe amorphous silicon that we used before. And by following a standard electron beam lithography and etching, we came up with structures as designed, where there were apexes hosting potentially high fields that can seed the process of nano trench formation. And after doing this experiment, which was a lot of fun, we were sending femtosecond laser pulses at the prefabricated sample in various experimental conditions, such as changing the pulse energy, changing the number of the pulses, the amount of total energy that was deposited on this sample, the polarization of incoming beam, and some other parameters. We came up with several different outcomes of the laser damage experiment. The first outcome was a little bit expected and a little bit less exciting, where if you use very strong laser pulses, the amount of energy carried by these pulses is enough to melt the nanoparticle so that the resulting nanoparticle has somewhat of a rounded shape and is not what it used to be, going from the initial nanoparticle and increasing the intensity, you basically melt it, and at very high intensities, it detaches through the process of ablation. However, for the second damage type, we found something that was unexpected in the first place, but then we found the explanation for that, and this is the nanotrench formation I was talking about in the first place. Now, this process looks to be dependent on polarization, so it really depends on what the polarization of the incoming pulse is. If it's horizontal with respect to the frame of the SEM image here, you see that the trench goes all the way vertically from the apex of the initial V to the end of the structure. But if you start changing the polarization, it will actually divert from the initial orientation and will go across almost horizontally sometimes. This process is dependent on the intensity. So the higher the intensity of the pulse you use, the larger the trench that you can get. So by carefully controlling the power of the mid-infrared laser pulse, you can come up with very narrow trenches that go as small as about 80 nanometers in width, and very high aspect ratio too. And it also is dependent on the number of shots that you send in. So you do need several tens of shots for this kind of trench to form. Just 10 shots will not do. We were somewhat we were trying to come up with an explanation for this phenomenon, and we came up with the idea that by generating dense semiconductor plasma, you can create very sharp, very localized local fields within the structure, and this is where the breakdown occurs and the material removal occurs, as you can see by these near threshold SEM images, where you are not melting the particle, but you are inflicting damage right at the apex, forming the keyhole type of modification. So here, basically, these are the preliminary results that I wanted to share with you, and the part of the reason I'm excited about them, and part of the reason I'm excited to present them to you today, is that I think there may be interesting ideas related to this kind of localized laser damage. Imagine you can put a living cell on this kind of nanostructure, on this kind of metasurface. Not only you can locally address some parts of the cell, some organelles or other parts of the cell with light that is coming in, you can also controllably deposit material near the part of the cell that you want to work with. I don't know exactly where this, this is a part of the discussion that I wanted to have maybe today, maybe at some point in the future. But just to mention is that this area of research is I'm very much excited about it, and especially because we've just established a collaboration with Dima Fishman and his laser spectroscopy labs, where we can send a controllable amount of pulse and electromagnetic energy to the samples. And these initial experiments have just finished yesterday, and we're really excited about the prospect of continuing this. So this, we're basically almost out of time. I would like to wrap up my talk by saying that today I hope to have convinced you that these nanostructures in general are a very promising platform for various photonics applications, including those that are related to all optical data manipulation, dynamic imaging, and the ways to come up with ultra sub-wavelength nanomachining and creating nanostructures with sub-wavelength resolution. If you want to learn more, please feel free to reach out to me. I am currently at Engineering Hall. My office number is 4412. I'm almost every day here on campus, so feel free to knock on my door. Send me an email at some point, and I will be very much excited to talk to you about your research and the ways that we can collaborate and do something outstanding. Thank you very much for coming today, and I'm open to have any questions that you may have left.
Thank you, Maxim. That's very exciting work. I think there are a lot of opportunities, and I hope you can start exploring those. Do you have time for some questions?
Yep. So I think that I'm meeting. The meeting is in 3 minutes, but if you have,
okay,
if someone has any questions, I'm more than happy to answer them.
I don't really have a question, but I mean, I just want to comment on the last thing. I thought that was very exciting, Max. I think it'd be super interesting to try and see if we could cut a cell that way, which is what we do in my lab all the time with normal femtosecond laser.
Mm-hmm.
But potentially that you could really get the scale down even more. You can really go to nanoscale that way, I think.
What would be the typical scale that you're working with, like a couple micron?
Yeah, I mean, so I think full width half maximum is like 100 nanometers on a diffraction limited beam. So, but that's, you could go, I think, smaller with that though, right? I mean, that's the size of the sort of the cutting beam, I think.
That's very good. That's very good. I mean, so
well, so you got to realize that that's not the size of the beam itself. That you can cut at a smaller size than the size of the beam. So actually, you know, in your system as well, you could cut at an even smaller scale than the size of the field. You know. Yep.
Yeah, that's definitely true. So we were working with mid-infrared beams for this particular project. So the trench width would be 100 nanometers, still very, very comparable to what you were doing. But if we scale this down to the wavelength of your laser, which I assume is visible,
Yeah. 1060.
Right, we can, so basically take your
Okay.
wavelength and divide it by about 10, and this is
Yeah.
where we can start talking, yeah.
Yeah. It's, I mean, you potentially can get really small scales then. And at that point, I start wondering what to do with it. You're sort of
Mhm.
on the scales of proteins and, you know,
Nice. Yeah, that's exciting. That's very, very good. Let's bring this up at some point and keep talking about this.
Yeah, I have a quick question. What's the dimension of the structure for the last portion, the wedge?
Yep. So this one is yeah, here's the scale bar. So here the single particle is about a micron in size.
Okay.
And this is dictated by the electromagnetic mode that we are exciting in it. So this guy here will be this hotspot here will be excited by the wavelength of 3.6 micron when the size of the structure is 1 micron. Now, if you change this to say 800 nanometers, reduce the dimension of the nanoparticle, and you'll get the very same condition.
Yeah.
But for a much smaller particle.
Now, one potential application whether they can enhance the generation of nanobubble, right? If you have a micron structure with a wedge, and looks like they can generate that high temperature at much confined space, whether they will be able to enhance the generation of nanobubble with loss threshold of laser.
Yes, I'm most certain that this can be done. Yeah, by putting it in a liquid.
Yeah,
and finding the correct power so that the local temperature is so that it crosses the critical value in a very small area.
Yeah,
I think there's no problem with this here. Yeah.
okay. Yeah, that will be interesting for
Absolutely. Yeah, it sounds exciting.
Max, real quick, I know you have to have your first meeting, but Christina put a question in the chat
about the circularly polarized light. I can see the question now. This is an excellent question. We haven't tried that yet. I think that what's going to happen is that it will still crack along the vertical direction, preferably, but maybe it will take more than 30 to 40 shots to complete the deal, because the vertical direction is preferable. And if you decompose your circular polarized light into two components, it will be the vertical component that will do most of the work. But that's just speculation at this point. We'll certainly next time we get back to this experiment, we'll certainly see what the circular polarization can do here. And also orbital angular momentum, you know, there are many degrees of freedom for light that could be used here and have not been used yet.
Right. Okay, well, thank you very much, Max. I think we have 2 or 3 meetings lined up, so I guess we should start those now. Aaron, how is that going to work?
So Jean-Ping.
yes, are we still stay in the same web?
Yeah.
Oh, okay.
Yeah. And then we have a 1:15 to 1:30 time slot. Tom, you and Sean should work out who wants to take 1:15 to 1:30 and who wants to take the 1:30 to 1:45.
Okay. Sean, can we swap? Are you able to do 1:30 if I do 1:15?